Okay, I can start, right? First, I'd like to thank Professor Stephen Larson and your group, okay, invited me to come to here and also arrange this talk. It's a very good experience. It's my great honor, okay, to visit your institute, especially long history of your group. And it's my great pleasure here. Okay, today I give this talk actually. It's the title of this talk is a sustainable approach to marine reclamations, a field trial in Hong Kong, and post-construction settlement strength prediction control. This talk is a very practical talk, and it's really important for Hong Kong. I will tell you the background later. Okay, and I can go down. Okay. So actually, which one? You know, push. Oh, here.
No,
not here.
No, try now.
Oh, you check. Oh, okay. You can see the contents of my talk. I don't want to spend time on this. And why I said this topic is important for Hong Kong, because you see Hong Kong is almost the most expensive place to own a property.
Yeah.
Okay. Almost on the top one. Okay. And there are 7.5 million of people, but the population is bigger than Sweden. You imagine, but the area is only 1,100 square kilometers. You almost 1/40 of the area of Sweden. A small area with a huge population. You can imagine the land, short supply of land for constructions, and you can see the demand for the houses in Hong Kong. And to solve the problem, okay, and one solution is to create a new piece of land for buildings, infrastructures. And you can see here, okay, you can see here, my mouse is here. This is Hong Kong airport. Professor Larson mentioned this is a new airport. Actually, all the airport is in the downtown, okay. And so this is Hong Kong International Airport. And finished in 1997, 98, okay? Started construction in 94 or 93, okay? And the government proposed to create lands here. Total area is about 1,700 hectares for about up to 1.45 million people. This original proposal, now government scaled down a little bit, only claim this area first, as phase one. Total area of reclamation is 1,000 hectares. 1,000 hectares is 10 square kilometers, okay, for nearly 500,000 of people. And the feasibility of this project has been finished. And for this area of reclamations, you can see the water depth, average water depth is about 8 to 10 meters water depth, but you have to create a dam above sea level at 6 meters above sea level. You can imagine a nearly 16 meters depth from the seabed bottom to the ground surface, 16 meters depth thickness. You have to fill it with certain materials. And how to fill these areas in the past in Hong Kong, we use sea sand. In sea sand, in the 20, 30 years ago, maybe people can dredge the sea sand in the Hong Kong waters, but it's all gone. No more sea sand. Then they try to search the sea sand in the neighbor waters in the South China Sea. It's almost exhausted. No more sea sand. Then they started to import sea sand for Yuanlan, and and other Southeast Asia countries. But some countries like Yuanlan, they don't want to sell sea sand. They want to use the sea sand for themselves. And also the distance. Okay, so those to find sea sand is also difficult. Then later, the people in Hong Kong use the manufactured sand. That means we have a stone first, then break the stone in the bigger gravels and further break down into the sand. We call this manufactured sand. Okay, manufactured sand. Okay, that's another solution. For example, for the third runway here, this third runway is finished, but not open in the operation yet. For the third runway construction, I think only 10% of the field material is sea sand. 90% of field material are manufactured sand. So you can see the price for the sea sand. Sea sand is more expensive. You can see the more expensive in terms of renminbi and Swedish the money is almost equal. A little bit more expensive. 15 or 20% more expensive. You can see convert. Okay, the renminbi to Swedish. What is it? The dollar or
crown.
A crown. Okay. You can see this how much for a ton. Sea sand is more expensive. Manufactured sand is a little bit cheaper. It's still more than 100. You can also convert to US dollar in terms of Hong Kong dollars. Okay, $1 is equal to nearly 8 Hong Kong dollars. Okay, you can convert. So in terms of cubic meter for sea sand, the price is Hong Kong dollar 410. Just the material only material. Manufactured sand is about Hong Kong dollar 280 per cubic meter. It's all money. Okay, 1 cubic field material is money that fills the area. The amount of the field material required is huge. You can imagine. If we use sea sand, manufactured sand, we need the money. Okay, for this area, the government budget, original proposal budget is 500 billion. Later, they increased to 600 billion. Later, they increased to 700 billion Hong Kong dollars. If people use this kind of sand and other methods, okay, like deep cement mixing method is also proposed, okay, for this reclamation project. I think the cost will be even higher than 700 billion Hong Kong dollars. And with the time, delay, the cost of material manpower will also increase. Okay, so you can see the cost will be huge. So we propose a new approach. This is a very practical approach. Say we call the PolyU, or university, okay, in brief, the Hong Kong University of the Hong Kong Polytechnic University, we simplify as a PolyU. In the last 5 years, I got quite big projects. Okay, so we propose a sustainable reclamation approach and also a combined ground improvement method. The first one, you want to know what's the meaning of sustainable reclamation approach. Okay, sustainable approach. Actually, we don't use sea sand. We don't use manufactured sand. Well, we use local dredged Hong Kong marine deposit, or the Hong Kong marine deposit west. Because construction seawall or excavation works, people will also dredge some Hong Kong marine deposit also west, dumping in some area. Okay, and we can utilize this kind of Hong Kong marine deposit west. Or we can also dredge the new Hong Kong marine deposit in Hong Kong water or the water nearby, or in even channels, navigation channels. And those materials are free. And we don't have to ship the material from a far distance. Okay, you can save the fuel cost. For example, we can also use other various wasts. Okay, like a construction waste, other waste which can be utilized, so that we can reduce cement use. We don't use sea sand or manufactured sand. Overall, together, we call this sustainable approach for reclamation in Hong Kong. And the idea is reconstruction seawall first. Okay, we need a seawall because you can see the proposed reclamation area is in the sea. Okay, so we have to build the seawall to surround the area, and we have existing marine deposit. Okay, I mentioned it before, the seawater depth is about 8 to 10 meters, and we have a marine soils in the seabed. The thickness can be a few meters to 20 meters, even more, depends on locations. So the soils in the seabed is also soft. It's a mixture of clay, silt, and sand, and some shale. Okay, so we to build a seawall first. We keep original marine soils in place. When we use a boat, dredging boat, to dredge materials, use hydraulic pump, then pump the marine soils, the marine deposit as a fluid, then pump into the area pump into the above the seabed to fill this area to the sea level. Normally, Hong Kong above sea level, 6 meters above sea level. the land level should be 6 meters above sea level. Okay, then we do this one. The problem is, the soil in the seabed is soft. Then you pump additional soft soils above is even more soft. Okay, not good for constructions. So we have to improve. And how to improve in time saving, cost saving manner is a challenge. Okay. So we proposed a combined. You see this is the second part. A combined ground improvement method is a combination of different parts of improvements. Okay, techniques together to improve it. So what's the basic idea? Okay, for this so-called combined ground improvement methods, you can see this is seawall, right? This existing soils which also need improvement. So the idea is we improve the soil here first. Here is a marine soil slurry placed in by hydraulic pump. So here like a liquid, the soil here like a liquid. Improve the soil first. How to improve the soil like a liquid, like a slurry? So we place horizontal drain first. Horizontal drain, you see, we place horizontal drain on the seabed surface in one layer. Then we pump in additional slurry above the seabed. We put a second layer of horizontal drain. Horizontal drain is the first drainage layer we place. Then we pump in additional slurry above. We put another layer to the top. Okay, this is the horizontal drains. Different layers. Number one. Number two is we can connect. We can connect all the horizontal drains to the pump vacuum pipes. Vacuum sucks the water out. Use a pump to suck the water out, and use a pipe to connect horizontal drains. Horizontal drains. Then use a vacuum pump to suck the water out. So the slurry will settle down very quickly. Okay, this is ideas. Okay, then settle down. Of course, we can pump in, build the settle down. Okay, the soil slurry settle down. Then you pump in additional fill on the top, maybe up to the seawall level. Then because you can see for the soil here, this is sea level outside. Soil here is above sea level, so the soil here above, especially the soil here above, can easily to dry because the slurry in that depth on the surface is above sea level, and because the sun, the heat, evaporation, and the soils on the surface can get dry very easily. So we can form a crust layer with high shear strength. Okay, so this idea with high shear strength. Okay, then we can go to second stage of ground improvement. When this cross layer is strong enough, the machine can go to the top. Then you can install water drains from the top all the way to the bottom. Okay, water drains. Then when water drains are installed, we can use a vacuum or apply vacuum to water drains. Or another simple way, we don't use a vacuum. We can use additional surcharge put on the top to compress the soils, increase excess pressure in the bottom, and let the water to come out easily. Okay.
How do you install horizontal drains?
Okay. Okay. You're good. Okay. Horizontal drains is a good question. Please wait for a few minutes. Later, I will show you animation how to place horizontal drains for so big area. Okay, later I will explain this to you. So the second stage improvement is we install water drains because the machine can go to the top. Then we can apply the charge on the top, so we can improve because for this layer of slurry, even though we use horizontal drains, we use a vacuum to speed up consolidation. The soil is strong, but it's not strong enough. So don't worry. We have a second stage of improvement. So we install water drains from the top always to the bottom. It's very conventional. I tell you, we install water drains. It's very conventional. And we apply the charge also very conventional. Many contractors can do so. And horizontal drains is a little bit new. And especially you ask me the question how to place horizontal drains and what the horizontal drains looks like. Okay, I will show you later. Okay, so then we do the second stage of improvement. So make soils here and here altogether, improve altogether to increase the shear strength, to increase the stiffness, to reach the requirement specifications. Okay, go ahead, please.
How you know the vacuum consolidation?
Vacuum.
Yeah, we used it like 30 years ago in Sweden. And failed every time. So
You mean failure?
You can get 100 kilopascal theoretically.
Yeah, theoretically.
Yeah, how much do you get actually here?
If we can, I will show you also answer your question in more details later.
Because so difficult to seal it.
Oh, yeah, that's another question I will answer you. We don't need the sealing. We don't have to seal the top.
Don't have to.
Yeah, we don't have to. So we don't have a vacuum leakage problems. You will ask me why. I will show you. I will show you the video later. We don't need to seal the top, so we can reduce the cost of place impermeable membrane and how to make sure membrane is no leakage, and so we don't worry about that one because the improvement of the slurry by horizontal drains and vacuum is a preliminary improvement. It's not a final stage improvement. Final stage improvement is we improve slurry after preliminary improvement and soft slurry on the bottom together by conventional vertical drains and surcharge. You know what I mean? So that's the idea. Then I will answer your question later, how to ensure the vacuum, how much vacuum can you achieve? And I will show you later. Okay, 2 questions. I remember, okay? Okay, so this is steps. One step, place horizontal drains, pump in the slurry, blah, blah. No need to go details. So important thing here is we use horizontal drains, we apply vacuum, we don't have to seal the whole area, okay? Okay, we have done many laboratory tests, including the cylinder test. You can see the test is very tall, very high. You see the 1 person. Okay, it's here. It's nearly 2 meters. Okay, here we put slurry on here. Slurry on here. You can see in the physical cylinder physical model test, the top no sealing. In the slurry, the vertical drain, horizontal drain is on the bottom. Horizontal drain on the bottom. If we apply vacuum, or at the bottom, okay, horizontal drain, okay, horizontal drain at the bottom, we apply vacuum at the bottom. So vacuum pressure here is the maximum. The vacuum pressure on the top is 0. So distribution of vacuum is a target distribution. Of course, what's the magnitude of vacuum here theoretically is 100. It's impossible in reality. I think if you in laboratory, we could reach 90 kPa is good enough. 80 kPa not too bad. 90 kPa in laboratory is very easy. In the field, maybe 85, 80 is okay. Keep in mind, for improvement of slurry is a preliminary stage. We can increase the shear strength to a certain value, but not all goal. We have a second stage improvement, okay? I show you the video. For slurry, we'll apply vacuum here, you see? You see, come down. Soft soil compressed. More than 60, 80%. We only apply vacuum at the bottom. And so as you can see, the soil is compressed from here to here compressed. Okay, the average vacuum maybe, in the target distribution, average maybe 40, 50 kPa. Don't worry about it. This is for preliminary improvement. We have a second stage improvement. Okay, so this is how we do. So we don't have to seal the top. So don't worry about the leakage of vacuum. Okay, that's some new ideas. Okay, and what the horizontal drain looks like? We propose horizontal drains in the grid format. Grid format, the spacing can depend on the design. Of course, this is another model test. It's a 2-dimensional plane strain model. No, it's 2-dimensional. It's 3-dimensional, 2-dimensional plane strain. And horizontal drains are in the grid format. Grid format is good. We don't have to horizontal drains like a plate, like a sheet. No need. The horizontal drain is even better because later we have to install vertical drains. So in the grid space, empty space, we can install vertical drains. This is just for preliminary improvement of slurry. You can see. So we measure pore pressure, we measure earth pressure, blah, blah, everything. This is after improvement. After improvement, then this is sediment. Okay, sediment. we measure sediment at different levels, okay? And the initial water content, okay, initial 200% is liquid. The of the improvement is about 58%. It's like a semi-solid, okay? You can see for cylinder test, two-dimensional cylinder test, the shear strength initially is 0. It's a slurry, it's 0. Then of the improvement, the depth also thickness reduced. Sorry about this one. And the shear strength increase gradually with time is more than 40 kPa. For more than 40 kPa, so it's quite strong enough. Okay, especially I will show you later. We can see a crust on the surface for machine. We can place machine on the top. This is for two-dimensional cylinder test. Two-dimensional plane strain test. You can see also initial shear strength near 0. Of improvement, you can see increase to more than 30 kPa. Okay, this is from 2 different types of physical model tests. To show you this one, actually from slurry, horizontal drain, vacuum preloading. We don't need to surcharge. Okay, we don't have to sear the top. Okay, so this is the idea. And so of course we need a prototype test. Physical model test, the size of model test is small. We need a large physical field trial in the field. So we got the government support. This is from government or university. AECON is an international consulting firm. Builder King is a contractor, and with support, many money is from the government. Put additional money, 5 million Hong Kong dollars. We choose a site in a new reclamation area. This is a pit, a big test pit. This airport here. This island is what we call, do you know, a very famous bridge, links Hong Kong to Zhuhai to Macau, 53 kilometers long link, tunnels and bridges, okay, for Hong Kong to Macau to Zhuhai. And this is a custom point. The people will come to here, go to custom, then go inside Hong Kong. This is island for that. This is a new reclamation for a new town development. An old test site is here. The size is quite big, okay? The length, 22.5 meters. The width is 18.5 meters. The depth of 3.5 meters. The depth of 3.5 meters. We put a horizontal drains in layers. We put a sediment plate to measure sediment. We also put the pressure transducers and even earth pressures. Okay, I don't want to go to details. Do all the instrumentation by my team. Okay, you can see off the field to the top, still like liquid. Then through the horizontal drains, we apply vacuum. Okay, all the horizontal drains are connected to vacuum pipes. We apply vacuum. Then this slurry become a semi-solid ground. You can see like a semi-solid ground. A semi-solid ground. Okay, and this is on the surface of the slurry. Okay, area. Okay, is on the surface, and you can see the shear strength in the crust. You can see the shear strength is quite high. Of course, below the crust, the shear strength is smaller. But in the crust, the shear strength is about 40 kPa. So it's good enough, strong enough for a machine to move on the surface. Okay, you can see the bottom, of course, the shear strength is also high. This is crust layers. Okay, because the slurry at this level is above sea level, and due to the sun dry, evaporation is easy to get a solid layer. We want to have this crust layers. Otherwise, how can we install water drains? Okay, so we have observed this one, a very good strong crust layers. You can see from slurry after initial 20 or 25 days, finally you can see the soil become very strong. Very strong. Okay, this is a small machine. Okay, we have done some calculations. 40 kPa is good for quite a heavy machine to be placed on the surface to install water drains. So now the sixth part is a cost comparison. I mentioned before the budget for the government before is really expensive. Okay, and we can compare the cost. Okay, using different methods. One is place slurry and the existing mineral soils improved together by vacuum preloading together. Second one, we can horizontal drain, water drains by surcharge. Another one is use a manufactured sand to replace the spot. use manufactured sand. I choose manufactured sand because sea sand, we cannot find the supply of sea sand. Manufactured sand, what's the cost? And some people want to use deep cement mixing to improve everything together. Use cement mixing method, even more expensive. We compare this method, and deep cement mixing to see the cost comparison. I don't go to details. I show you the unit cost, even better, unit cost, okay? If we use a dredged Hong Kong marine deposit, a horizontal drain, vertical drain, vacuum prenodium, the unit cost only 36 Hong Kong dollars per cubic meter. 36 divided by 8. Only four US dollars. It's only a few US dollars per cubic meters. If you use the manufactured sand, it's 280 Hong Kong dollars per cubic meters. Okay, and if you use deep cement mixing, even more expensive, 317 Hong Kong dollar per cubic meters. So you can see the cost.
Have you calculated on Japanese technique for the airport? They pump sediment and introduce cement on a band.
In the band, okay.
Yeah. So it was, what can I say, factory manufactured. So when pump, all the material was stabilized.
Okay.
Before it hardens, you know.
Okay.
Pumped material. But
yeah.
I don't think you can decrease it.
There cannot be just cost. That's also not. That's also expensive. And some people, Japanese people, they mixed slurry with cement first on the barge, then pump it into the seabed. That also needs cement. You have to have enough cement. So once you mix, you need a manpower, you need a machine to mix. And you add cement, that's the money. You increase the material cost. I don't think that's maybe very close to this one. Okay, deep cement mixing. Maybe very close to, maybe a little bit cheaper, maybe close to this one. Not cheaper. Then we just simply use dredged Hong Kong marine deposit by vacuum prenodium, by horizontal drain, water drains. You know, I don't think it's cheaper. Should be more expensive. Okay, so you can see if we use our approach, use our method, it's very cheap. A fraction of this cost, 280 or 317. The cost can be reduced a lot. Okay, this is a cost comparison. Okay, I don't go into details. And then for the whole area, how much you can save in unit cost. Is easy to understand. Okay, for other one, just calculate certain areas, how much cost we can save. We can save billions of dollars. Okay, I don't go to details. Okay, no worry. Go back to your question. I mean, horizontal drains. How can we place horizontal drains for a large area? Maybe 100 meters wide, maybe 100 meters long. People cannot go there. It's slurry, like liquid. Okay, how to do this one? First one, our horizontal drains is in the grid format. You know what I mean? You can see a schematic diagram here. Say we have a length, maybe say 100 or 150 meters, and you have widths, maybe 25 meters. You can make this in a row in the smaller size. You can transportate a row of horizontal drains for the manufacturer plant to the site. So easy to transport. Okay, that's number one. Okay, in a roller, like a roller. Okay, second one, we can place this one. I have a small animation here. You can see. See, this is width. The roller, you can use the ropes, something to put on one surface. No need for people to send people to inside. Okay, the ropes you can on the shore, you can pull it. One layer by one layer by one layer constructions. Very easy to place horizontal drains. So this is some new concept from us. The first time we propose this one. You know, some Chinese people in mainland China, they also use dredged marine soils or subsoils as a fill material to fill a reclamation area. China has this ideas already. They have done such projects successfully already, but they use a different method to improve the survey. They use water drains. Okay, for this layer, for this layer, slurry use water drains. But the slurry is a slurry. So how can we place horizontal water drains? They use a boat. To go inside. They use the manpower to insert. Okay, you can imagine the slurry can settle down by self-weight construction. Maybe on the surface, it's very soft. Maybe near the bottom, it's also strong. Hey, go ahead, please.
Yeah, I was thinking about this is probably something you will talk about maybe.
Okay, yeah, go ahead.
First, it will be normally consolidated.
The soil, the soil in the seabed in the original the Hong Kong marine soils is from normal concentration to over concentration 1.2 or 1.3. Not heavy, not heavy. Hong Kong existing one.
We very often talk about 1.3 in Sweden.
Okay.
To get rid of the enormous creep.
Okay.
And if you build an embankment, the surcharge is very high.
Okay.
So we have trouble. It can be difficult to find the material.
You mean to fill?
Yeah.
To fill the embankment. Okay. To surcharge. Okay.
Get 1.3, especially in the bottom.
Okay. That's the question. I will answer your questions later.
Okay.
What over concentration ratio we need to improve soil? I will show you. It's a good question, Professor Nelson. Okay. Okay, go ahead.
I don't understand if we have the slurry layer already. So how do you inside this layer put this horizontal?
It's a question.
This one is one layer by one layer. For example.
But now it's there.
For example, this existing seabed. We have to put one horizontal on surface. Maybe this distance, maybe it's 100 meters, maybe 150 meters. Doesn't matter. We can put a roller of horizontal on here. Then we can put to here, the place on the surface. Then we can pump in additional slurry on the top. Suppress it. Additional, it's very easy. The hydraulic pump, you see the video at the beginning before the hydraulic pump is the force very powerful. We can pump slurry from maybe 100 meters, 200 meters away to inside. No need for you to go inside the pump.
How fast is how long time does it take to fill up the?
Depending on the energy of the ships. Some ships has a very large capacity. The video I show you, that ship is the largest one in Asia. But Netherlands is another country with a very large this kind of dredging boat in Netherlands, probably number one in the world. But China has the largest dredging ships in Asia. Okay, the one I showed you before. If I remember, the capacity is 6,000 cubic meters per hour. 6,000 cubic meters per hour. With a very large capacity. It's no problem. Okay.
A short question.
Yeah.
How do you control the thickness of the layer?
Thickness is I think it can be measured or can be by experience, observation, and measured. Okay. It's not. I propose. Depending on the property of the mineral soils, depending on the permeability and so on. Okay, I propose about 1 meter to 2 meters, 1 meter to 2 meters. If 2 meters, you can imagine 2 meters can be compressed 60–80%. 2 meters can be compressed to only 1 meter. So finally, I think about 1 meter to 2 meters in the between. I mean the thickness of slurry, or in my experience. Okay, the thin layers. You place more horizontal drains, you can speed up consolidation faster. Then you need some calculations. This is my experience. 1 meter, no more than 2 meters. 1 meter to 2 meters. Okay. Now, then go back to I will ask Professor Nelson's questions later. Okay, and regarding the improvement of the soils, so especially soils, you have to have a certain knowledge on the basic properties of the soils. Okay. For example, the soft soil in Sweden will be different. The soft soils or marine soils in Hong Kong. Here, I just show you some comparison. For example, Hong Kong marine deposit, number one, Tianjin marine soils, either in the north and the east of Beijing. Okay, and the Tianjin soil, marine soils, then Dalian is further north, very close to Korea and Japan, Tianjin. Okay, you can see the Hong Kong marine deposits, the property of Hong Kong marine deposits, actually, in general speaking, better.
Much better.
Much better, yeah. You can see much better than you have experience. Then the soft soil in Tianjin and Dalian. Why? Because the minerals, this is very important minerals. Hong Kong mineral deposits only have minerals, kaolinite, illite. But the soft soil in Tianjin, Dalian, they have a mix of illite and monazite. This is trouble clay, trouble clay. Okay, trouble clay. You know, nuclear waste disposal. They want to use a motorite or bentonite. Okay, because the probability is very, very, very low. When probability is very, very low, then the water very difficult to come out. So it's some difficulty. So fortunately, Hong Kong metal deposits, the properties are better in general speaking, but better. Also, the clay contents is less compared to the soft soil in Tianjin and Dalian. But I don't know what the composite of Swedish clay.
Nothing, Carolina. We have
Similar to
almost everything.
Oh, the inite. Okay.
Mostly.
Okay.
But some shit into this also. This is
troublesome. Oh yeah, that's troublesome.
But this one never.
It's better. Okay. The inite is in the middle.
Yeah.
Okay. This one is the better. Okay. This one is the worst. Okay. It's the worst case. Okay. And so you can see to improve Hong Kong metal deposits, actually, we should have confidence. Okay, to improve the Hong Kong metal deposit. Okay, we should have confidence. Basically speaking, properties are better. And
sometimes we actually here have 10 minus 11 sometimes.
Okay.
Then you have a spacing with drains are like
1 meter? Or?
No. 50 centimeters.
Oh, okay.
So I mean, but we are very often here.
Okay. So it's Hong Kong is better than Swedish clay. Okay. So I did some study on Hong Kong metal deposits with a long history. Okay, so I published a paper regarding Hong Kong metal deposits with different clay content. The clay, more clay and less fresh angle. So we did some correlations before. I don't go into details. So the clay, the content of clay will affect the effective fresh angle. More clay is more trouble. Also, the stiffness is also smaller. Okay, so that's some ideas. Another one probably go back to you, and we also did some study on cement mixed Hong Kong metal deposit before. I started some laboratory studies in 1998, mixed cement Portland cement powder with the metal deposit at different percentage. And later I have another students dug the hole and did a PhD study in this area. We found a really good correlations between water cement ratio and the unconfined shear strength. This is really good correlation for Hong Kong metal deposit. Maybe for other soils, maybe different. But the trend correlation formula maybe can be used. Okay, you can see more initial water content. This is negative power, so less unconfined shear strength. When the initial water content is high, you put the same amount Portland cement, okay, build negative. Is the shear strength. Unconfined shear strength is small. So this is really good correlation. Is the reverse. Correlation is for Hong Kong metal deposit here, reverse. But you compare to clays in other countries, like Singapore clay here. Singapore clay is not good clay. You can see for the same amount of the ratio, the unconfined shear strength is here, below the Hong Kong metal deposit. And Bangkok clay is in the middle. I don't know which part. You have to refer to the paper. For Japanese clay, actually is the better. It depends on the location, where the metal deposits, okay, in the Japan, okay. But in general speaking, Hong Kong metal deposits is not bad. For the beginning, also mentioned to you the reason, because the clay minerals, okay. Recently, my students, Dr. Chen Wenbo, and he did a serious study to mixed, so archive activated incinerated sewage sludge ash. This is for Hong Kong, because we burn the sludge, then we have a byproduct ash. Okay, so we have to utilize this kind of ash. So we can mix this one with metal deposit. You can get some ratios.
But you will never have enough, or
not enough. But we can utilize the waste. Okay, so we can utilize, but certainly for reclamation, not enough.
We have used ash and blast furnace slag for 30 years or something.
Okay. But you have a very good steel
industry.
Yeah,
but long transportation.
Oh,
and they realize now that they can take much more money for each ton. Before it was more or less for free.
For free.
They have mountains.
Yeah, mountains. Yeah.
But now it costs a lot.
They have to sell, they have to pay for that.
So they now make business.
It's a new business idea.
That's true, that's true. I tell you, the second one is activated granulated blast furnace for steel, making a plan. In China, this also you have to buy. This product. So maybe similar to Sweden, you have granted. This is some kind of coarse particles like ash. You know, this one you have to buy. And you have to make it granted into the ash, then mix this one into the soils, add some lime, some other.
So lime is an activator.
Yeah, it's activator.
Not cement.
Not cement.
Okay.
In this study, no cement is used. No cement, you only use lime to activate the shear strength. Okay, this is done study by my student. Of course, we can also mix this one and with cement. Cement is also okay, but cement in this study actually they just don't use cement at all. It's also can be done.
How much? We have 20% or something.
Okay, you can see the proportion here. Okay, the RSSA, that means this one, CTPS, this one, 30%. 30%. And nine is 9%. The mix in terms of dry mass together, we can get the unconfined shear strength with the water band ratio. Band means this two together. You can see this green one. Even higher in this area, even higher the cement mix the soils can reach the same shear strength. But you can see this green one, no cement at all. But is the shear strength still good enough for this ratio? Or beyond this ratio, below the cement, improve the soils. So we have done some series of laboratory studies in these areas. Okay. Go ahead.
Actually, on the figure, you showed relationship between the compressive strength with the water binder ratio.
Yeah.
But here we don't see how the percentage of the soil affect the strength. Normally, I think the binder, water, and soil should be. So
yeah, you can see the binder means the RSA is together 30%, 9% lime, then 39. 100 minus 39 is the soils. 100 minus 39 is 51. 61 of the total mass.
Yeah.
In this compound is the soil.
So that means in the empirical equation, the W over C that is based on the weight is not the volume.
Which one? This one?
Yeah, the correlation by.
Okay, this correlation is for cement only, but here the comparison is similar to this one. Similar to this one.
But if you change something, if you change soil and change cement type or binder,
we will be different.
We have very bad correlations with cement, water cement ratio.
Okay.
You're all over the place in the graph.
Oh, really?
Yeah.
You have to make sure.
It's very sensitive.
Oh, very sensitive. But yeah, you can see the huge change, then the slow down. So you can see also some scattering here in your study.
But the main issue is that we decide the binder content and type from laboratory test.
Okay.
And then you get totally different in the field.
That's true.
The correlation here is plus minus 100%.
Okay. You know why? One, in the soil, in the laboratory, the soil is very uniform. And the binder soil mix also very uniform. In the field, just use the agar to mix, you are not really sure it's that's so uniform. Some voice, some spot, no cement at all. So it's the uniformity, and that's number one. Second one is the soil in the field. And the soil you do the laboratory test, maybe not exactly can represent the whole profile in the field studies. So this correlation for laboratory test is a reference only. So in Hong Kong, they do the field coring, do the coring to take samples out, they do the laboratory test, and to check what the percentage of cement, percentage of soil, what the water content, to verify maybe this correlation needs some correction.
But it's better with the slurry. We have all the dry method.
Or use the dry method, the dry powder.
The main difference here is like in the laboratory, you compact the material.
Yeah, yeah,
in
yeah.
layers.
Yeah,
And
yeah.
you don't have this procedure in field.
Okay, you're right.
Totally different.
You're right.
And here you mix the small clay, maybe 5-10
Okay,
minutes.
you're correct.
Yeah, in the field you mix like seconds.
Oh, yeah, yeah, yeah. You're right. You're right.
So I mean, it's not the same material. I mean,
Yeah.
so I say that skip the laboratory test and focus on field test.
I'm
I'm the only one. I'm the only one in Europe on that side.
Okay.
But the laboratory guys, they are the rest of the people. 99.
against you.
I'm the only one here.
Okay.
But we have so much data that the strength itself, the magnitude in the laboratory is crap.
Okay.
You know, there's a new paper from Finland
Okay.
published just a couple of months ago.
Okay.
They tested 5 laboratories,
Okay.
the same soil, the same binder,
Okay.
and they told them use the standard.
Okay.
What do you think the scatter was?
Okay.
I can say within the laboratory,
Okay.
it was like ±5%.
Okay.
So you know,
Scattering. Okay.
Really?
Small.
really, but between the laboratories,
Okay. Oh, even between 5 different laboratories.
so
Yeah, some
there's
differences.
no scatter in the laboratory,
Okay.
but between the laboratory, 250%.
Oh, difference. Okay.
Yes.
I don't know the reason.
Yeah, that is happened. That's happened.
I mean, and we did a study in Sweden long ago, just the conference paper, and we got the same result.
Okay.
But this paper is in Tekniska testing journal.
Okay.
the
Okay.
Finnish study.
Okay. Oh, no. Okay.
Yeah. I think it's similar to I did one study before about the binder.
Mhm.
When I started to do like 5 tests, we see really much different in the results.
Okay.
Even we follow the same process. So after that, we have to do another roughly 20 sample to check it if they are quite uniform. If it's not so, finally it doesn't show any meaningful.
But you see there, you can be, since there is no scatter in the laboratory, you think everything is very accurate.
Okay. Okay.
But you have a bias here, enormous bias.
Okay. Bye.
And actually another, because I think in the past, almost researcher or even the quite famous professor, they just only focus on the water binder ratio.
Okay.
They think this is the main factor.
Okay. Okay. Yeah.
But and then when I did my study, and then I see not just only water and binder, but the air and the soil volume also have an effect to the strength. So normally they shoot the 4 component in, because I think the water over binder is not enough, the good index to reflect the strength.
I agree, because we have sulfide bearing clays in Sweden. It smells like rotten eggs.
Okay.
And I mean, the strength development here is extremely slow.
Okay.
You have to wait like 3-4 months.
Okay.
But for lime and cement in normal clay, it's like 2 weeks.
Okay. Okay.
So you see, the type of soil has an enormous influence.
Agree.
And we see that different qualities of cement.
Okay.
If you take a cement that is older, dry, and you take the fresh one,
Oh.
it's a difference.
Okay. Okay.
Yeah.
So if you take a set, 1 year or so,
Okay.
and another one just bought,
Okay.
then you will have different.
I agree. I agree with you. Maybe water cement ratio maybe cannot reflect all the factors, influence all the factors. I agree.
But maybe you have core drillings, test pits.
You mean?
Do you take samples? From
Yeah, we take samples. Yeah.
Yeah, those are very good.
Yeah. For real projects, for example, for third runway, deep cement mixing was used for existing soils.
But
above is
how do you take the samples in the clay here? The stabilized material in the upper part here. Core drilling, or how do you do it?
coring.
Only wet grab
You-
sample, or?
You mean how to do the coring?
How to collect the sample.
It's easy. They do the drilling, okay, all the way from the surface to the in the real project in Hong Kong for the third runway construction, all the existing marine resource, 80% or 70% of existing marine resource was improved by mixing cement with existing soils. The above seabed is filled mostly by manufactured sand. Then answer your question, how to take soil samples from deep cement mixed the soil ground. You can do so even before you paste the fill materials. You in the barge to the drilling, to the cement mixed soil seabed to the drilling, just like ordinary soils. What we use as messy assembler. Messy assembler is a very thin the tube sampler, and the diameter is about 75 millimeter, 74, 75 millimeter. Messy assembler. So it's a conventional way to take soil samples. Okay, in Hong Kong.
It's good size.
Yeah, it's a good size. 75, 74, 75. As I said to you before, laboratory data is a reference. Okay, it's a reference. But for the real case, you have to do the coring to check the quality, whether or not the shear strength is reached or not. So it's a checking. So if it doesn't meet the requirement, they have to redo it. So you can also check the quantity of constructions, mixing quantities. So it's a final checking stage. So don't worry. Laboratory data correlation or accurate or doesn't matter that much. They will do the checking later. Okay. Is that okay?
Yeah.
Okay, thank you.
I have a project at the moment now where we actually have calibrated the column penetration test. Do you know about that?
Column penetration.
Yeah,
What do you
it's a
mean?
wing actually. We developed it in 1979 or something.
Okay.
The problem has been that we never wrote about it in English.
Okay.
It's only Swedish.
Okay.
So it's a Swedish method, but now we have started to write about it.
What's the meaning? What the column penetration is for?
It's a wing.
It's a wing.
Yeah, you just push it.
Okay. Or the similar to auger. You mean?
No, not the auger. It's like this.
Or in the plate.
Yeah.
The plate. Okay. The put in.
So if it is very stiff,
Okay.
the problem is that you fracture it. So
Okay.
troublesome failure mechanism.
Okay.
But if it is like 40, 50 kPa or something, you get actually bearing capacity failure around the wing.
Around the wing.
So then you can use a bearing capacity factor.
Okay.
And we always use it as a control method because you can do like 7, 8 per day with one machine.
Okay.
So it's a pretty quick one.
You mean use a plate?
Yeah. Then we have a CPT probe in the bottom, so you actually measure the resistance.
The CPT
against the blades.
Okay.
We have done now a calibration test in Norway.
Okay.
Just now.
Okay.
With the slurry cement kaolin.
Okay.
And more or less the same properties as in field.
Okay.
And we have done tests, and this material is almost homogeneous.
Okay.
There is no scatter.
Okay.
So we have calibrated now the penetration test.
Okay.
And we get the bearing capacity factor, depending on the surrounding pressure and several things, between 7 and 28. 400%. Depending on the surrounding pressure,
Okay.
horizontal pressure. So it's a huge influence, actually.
Okay.
We're doing field tests now after, in January we start.
Okay. 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 So I hope you can write a paper.
Yeah.
Then people know.
Absolutely. We have a paper now with Prof. We intend to send a Canadian Geotechnical Journal in about a month or something.
Okay, you mentioned Canadian Geological. Okay. Okay. The second, the number A subsections is how to predict, control, post-construction sediment. This is a very important topic. So once you improve the soils, finally you have to make sure sediment, especially post-construction sediment, is not big, is within the range, not too big. Otherwise, in the future, you put buildings or pipelines, utilities on the soft soil ground above, you have trouble, cracks, differential sediment, blah, 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 some troubles, you know what I mean? So how to predict, control the post-construction sediment is very important. Then go back to my previous research. Okay, they are how to control. You have to predict first. At least you do some initial calculation. Okay, then you need methods. Basically, we have two methods. Okay, one numerical methods, another one simple methods. Numerical methods, probably you know that very popular program practice. Okay, practice, and because for soft soils, you have to consider nonlinear behavior, elastic, viscoplastic. Especially you want to consider creep. Okay, we want to consider creep. So you have to apply a soft soil creep model in practice program. And this soft soil creep model is actually an elastic viscoplastic model. Elastic viscoplastic model. This this abbreviation was used by me a lot. Okay, in the past 20, 30 years. This model is almost the same. This model was proposed by me, This proposal actually in the program. Okay, but I know the people on the back is Peter Vermeer. Okay, they know this one. But the two models are very similar. Okay, and you need a commercial program. You have this commercial program. My former students, he also wrote another computer program, but not commercialized. And some other professors in USA, they have some programs for free to use. You can search for this. Search. I sent an email to him. He said it's free to use. The model he used in this program is very similar to this model. Okay, he mentioned to me a professor in USA, free to use. Recently, okay, I don't go to details, and I have done research on this with a long history. Started from my PhD study. I don't go to details. We also have applied this method for some field embedment analysis. More recently, we have the simple methods. Okay, this is you need a commercial program. You need the knowledge. There are many parameters. Professor Stephen mentioned to me some models need 16 parameters. Okay, and engineers don't like it. For some soil model, maybe 8 or 10. I don't remember exactly. Okay, it's also difficult for people to use. Engineers don't like it. So recently, in the past few years, we propose a simple method. So engineers can do hand calculation or use a spreadsheet program to do calculation. That's something new. Okay, the simple method here. And if you read our recent paper in 1917 and also a more recent paper in 2022, you can see my simple methods can be done by hand. Okay, primary constellation, creep, all the items here can be done by hand. Yeah, this is really similar to the old methods. What we call hypothesis A method, but this is a hypothesis B method. It's very simple to use. How many parameters, Professor Stephen? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, we still have 8.
But CRCC.
But those are very conventional.
Yeah.
All conventional engineers know it. This is a recompression index, normal compression index, pre-concentration pressure, secondary compression coefficient. People know it.
Yeah.
And the time is 1 day because we, from odometer test, we get this kind of curve. Vertical strain, horizontal, the vertical stress in log scale. The point here with 1 day duration already. The odometer test, multi-stage odometer test with 1 day duration already. So it's automatically 1 day. Don't have to make decision. Voice ratio, initial voice ratio,
Yeah.
people know it. So here is nothing really new. This 2 parameter is a little bit new. It's a little bit empirical. How to get it? How to get it? This 2, why the alpha, beta choose 0.8, 0.3? Because it's a little bit empirical fitting because we compare these curves I show you later. The sediment from this simple method with a more accurate modeling from practice. Practice is more accurate. Okay, this is simplified. So we compare the simplified method results curves with curves from practice. Compare, then we choose zero, adjust the 2 values to fit to compare 2 curves. We choose 0.8, 0.3 is the best. Okay, actually for different soils, maybe we will vary a little bit. You can study. But in the future, if you have a chance to work on soil soils, you can try. This may be vary a little bit, maybe 0.7, 0.4, also okay. So it doesn't matter, but the whole structure here is very simple to use. I don't go to details. And recently, this simple methods and the previous one, the numerical methods, I have proposed to be adopted by the Canadian Foundation Engineering Manual, published in December 2023. So accepted by the Canadian Foundation Engineering Manual. Recently, I talked to the people in Norway. I hope Eurocode. I hope, okay, not easy. I can consider our methods in Eurocode. Because in Eurocode, I studied Eurocode before. They mentioned we have to consider quick. You mentioned a few sentences, okay, but how to consider, no answer. So I hope Eurocode can borrow some ideas from the manual we published already. This is the first manual which accept my 2 methods. Actually, for the first method, actually it's there already. You know, sorry, this one. Let's go back. Sorry. Oh, numerical methods. Actually, you use this already in Europe. Very popular in Europe. Actually, this method what is also in Canadian Foundation Engineering Manual. You have to choose a proper model. This model in the practice already. So this method has been used, but not in the Eurocode. But this method has been presented in the Canadian Geotechnic Foundation Engineering Manual very clearly. You have to use the methods with a proper considered model. But in Eurocode, not mention this one, but this method has been used in Norway, at the UK, in Germany, has been used already, but not included in Eurocode. Okay, I hope in the future this can be included in the Eurocode. Okay, in the future. Okay,
But
so
you don't state exactly.
No, so probably it could be used. The requirements are a little bit on a higher level, but there could also be national guidelines on how to fulfill the Eurocode requirements.
Okay.
And in those such guidelines, these could.
In the guideline you can put more details.
Yeah.
You're right. That's what you also mentioned today. You want to present the guidelines for the local area, like your countries. I think in the future, if you have a chance, you can think about this one. I talked to some professor in Norway.
We have, a soft soil creep.
Yeah.
We have, I told you about Minna Karstunen at Chalmers.
Yeah.
She reject this one over and over and over again.
She reject.
Yeah, she's shown that this model doesn't work.
Which one?
Hate it.
Which one?
Soft soil creep.
Soft soil creep model.
She hate it.
Okay, really?
Motivation for her to develop.
I didn't know this one. Why she hated it? Maybe I'm wrong. I guess.
The reason is her one S clay creep. The name, yeah?
Because she developed elastic visual plus model in Peru.
And that's the only one that works. No others. And they are the only one who can handle it also. So all clay tests must be performed at Chalmers.
By Chalmers.
In the world. That's her idea.
Okay. Actually, I tell you, my students use this quite a lot. This model, my model, very similar. I have another PPT showing the difference, very similar. In general speaking, the soft soil model is good, but there are some limitations. You must be careful. Beyond certain time range, a certain pressure range, maybe some more errors. Okay, so you have to consider apply the model for certain range of pressure, certain range of time. If the time is infinity, you have some trouble. So actually, in my more recent works, we have improved this model, my model, to consider a longer time, consider high pressures, and we have a new improvement, but which are not included in the soft soil creep model. Okay. Generally speaking, it's okay, but under some extreme case, maybe some more errors. Okay. Maybe don't go to details. And the final one is how to control. And I will answer Professor Stephen's question. How to make a soft soils over-consolidated, maybe 1.3, maybe more. So you have a good experience. You mentioned 1.3, the same number I hear here. Okay. So for how to control post-consolidation sediment, prediction method, calculation method is one, and how to control it. Make a post-construction as small as possible. One simple, also very easy way is to make soft soil over-consolidated. Okay, or maybe for the young people, you don't know it. Just surcharge more. Then remove the fill, then the post-construction is small. Okay, so idea is, okay, it's here. If this is initial stress, okay, you have a design node here, For example, design node depending on the structures, maybe traffic, blah blah. Okay, you have certain design node for Hong Kong runway. For Hong Kong runway, the design node is about 40-50 kPa. Okay, for example, the design node. So initial stress, you apply design node, then you note this strain, the stress, node here to here, from originally maybe over consolidated. Go past the pre-consolidation pressure to here. This point is in normal consolidation line. So you can see the compression on the design node from here to here, this big. That's a elastic plastic compression. Then you have a creep. When the point is in the normal consolidation point, the creep is very big. Okay, very big. In the over consolidation point, the creep is small. So without additional surcharge, the sediment will be here and here is very big, okay? But if we over surcharge the soils, okay, we'll apply more surcharge to here. So that means come here to here, then unloading to here, unloading to here. Maybe you cannot go to original point. Due to surcharge, I will experience more. After unloading, maybe you not go to the original because you have some sediment. You have the compensated sediment. You have to keep some fields remain on the soils. So the initial point maybe after unloading cannot go back to here. But after unloading, compensate the sediment up to here. Then you can imagine this is a new initial point. Then you apply the same design node of here, maybe to here, here to here, maybe to here a little bit. Okay, the same design node to here. You see. Immediate compression is more elastic. It is the over-consolidation line. Then here, this point is a new pre-consolidation pressure point. This is the old one. This is the new one. This point is below this one. So this point actually is in over-consolidation state. Then this immediate compression is small, creep also small, overall is small. Especially the post-consolidation sediment is more related to creep, is small. So just make sure over-consolidated. You don't need any binder. You don't need the cement. Just do the surcharge and remove surcharge. You have this point. You can reduce the post-consolidation sediment. The problem is how do you make this point here, or here? How far? That's the over-consolidation ratio. The stress here, the ratio is called over-consolidation ratio, OCR. OCR is the stress. How to make this OCR, over-consolidation ratio, and the 1.3. In Hong Kong, people sometimes use 1.2. And the Professor Stephen mentioned 1.3. I propose 1.3.
We have 1.15 in the old guides.
1.15.
1.15
or 1.15. 1.15.
It doesn't work.
It doesn't work.
Huge.
It doesn't work. It's a huge amount of post-construction sediment. 1.15, even below 1.2, is not good enough. Hong Kong before they used 1.2, but recently the director in AECOM, he said should be 1.3. I suggest 1.3, even higher, 1.3, even higher, at least 1.3, because if the structures are very sensitive to the post-construction sediment, the higher OCR is the better. The high OCR means this point should be moved here, move here, you move here. Close to 1, close to here is 1. Inside a little bit, maybe 1.15, 1.2, you know what I mean? Yeah. Really close to here, the normal concentration line, 3 is really big. So you're right. 1.15 maybe doesn't work. Okay. So this is how to control, control the post-construction sediment. Really simple to make the soils over-consolidated. And this is the control parameter. And after vertical drain, horizontal drain, I mentioned before, to improve the soils. Vertical drain, horizontal drains, the purpose is to speed up consolidation of soils. And we have a parameter, what we call the average degree of consolidation, to indicate the consolidation is finished or what degree, of consolidation. So use U average. U average can be defined in terms of average pore pressure, also can be defined in terms of sediment. If the soil behavior is elastic, the two definitions give the identical value, the same. But if the soil behavior is non-linear, especially with creep, the two parameters give a different value. Okay, so be careful when the soil is going to go to non-linear, two may be different. Okay, so you maybe have you apply two. Okay, I mentioned before when you compress it, and some soils you cannot remove the whole surcharge. Some fill material will remain because the ground is settled. You have to maintain the same ground level. Some fill material cannot remove all the fill material. Some fill material will compensate the sediment will remain. You'll remove the part of the fill materials. So your calculations should consider the fill material remained. Okay,
but it's extremely sensitive to the groundwater. Okay, it's included in a project like 20 years ago. we built the road on, the strength of the soil was like 2-3 kPa under shear strength. And we actually installed drains there. So 3 meters of settlements.
Okay, 3 meters. Okay.
Yeah, 3 meters. And it was really, 1.2 over-concentration ratio, and everything was nice. But suddenly we had a very dry summer.
Okay, very dry summer.
And you had a pit here who pumps for drinking water.
Okay.
So this summer was dry, so they pumped more than
The
usual.
water table go down?
And it went down 5 meters.
Oh, 5 meters, a lot. That's a
So
lot.
the road here,
Oh, sediment, okay.
we got 30 centimeters just during the summer.
Okay,
And there was almost a claim now between us and the client,
okay,
because we had a design for this one,
okay.
and now it's set to this one.
More, they complain.
But we could prove,
Okay.
because we had piece of meters
Piece of meter.
long way from the road,
Okay,
where you can see that 5 meters drop.
okay.
And then we asked the community for a data of pumping, but all the data was gone this summer.
Okay,
So they have actually pumped too much.
okay.
So it was several kilometers were like, we used 1.5 million meters vertical drains. So you can imagine now we had a huge problem here.
Okay, that's a huge problem, okay.
Yeah, actually
5 meter water table going down. That's
But it was
50
interesting,
kb
we had a small,
surcharge, 50 kb surcharge.
they had a small part, 5.5 meters with deep mixing columns,
Okay,
just test columns.
okay, test corners, okay.
Yeah, so we had a road now.
But not sediment for the cement corners, okay. Okay, pump, okay. Yeah, good experience, okay. That's something very important for young people, okay. Water table drawdown can cause a huge sediment.
But
Okay.
they installed the columns, test columns,
Okay.
in the middle of the road.
Okay.
I mean, they should have performed.
Yeah, so the roadside, okay, not in the middle of the road, okay, very strange. So how to control sediment, make sure over-concentrated. Okay, so it's really simple, okay. And I have done some calculation, one example, don't go to details. In order to achieve OCR 1.5, for example, I do a simple calculation here. This is a PPT I can lift here. You can share. Okay, my PPT I can lift here. You can share with your colleagues. If you want to achieve OCR 1.5, what the surcharge we need, and how much surcharge we can remove. I have a simple calculation, hand calculation here. Okay, you can think about it. Okay, I don't go to details. For example, for this case, I need to fill thickness, 6.42 meters fill in order to achieve OCR 1.5. Okay, if for OCR 1.3, this can be smaller reduced. A simple example, calculation examples here for you to refer to. Okay. And even more, okay. And another very important issue is how to check the quality of soil improvement. I mentioned your different technologies, right? Horizontal drains, YTP loading, vertical drains, surcharge, blah, 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 right? How do you make sure the improvement can reach your requirements? Okay, one simple way is to do wind shear test. Do the wind shear test. Wind shear test is very good for soft soils compared to cone penetration. So do the wind shear test to check the on-joint shear strength. Okay, if the soft soil is improved to certain value, then CO should be high enough. You can specify CO required of the ground improvement as a consultant, as a client. Okay, you can specify this one. Okay.
Sorry, I have to go to a meeting.
Okay.
But then you'll take you to lunch.
Okay. Thank you very much. Okay.
I joined you after lunch for the Vasa Museum.
Okay, thank you very much. Okay, so you can check the quality of soil improvement. Okay, as a consultant, as a client, you make sure the contractor can do the right job. Okay.
So CU is the coefficient of uniform.
No. CU is the on-joint shear strength. Sorry, it's on-joint shear strength.
I see.
It's the shear test. It's not the the symbol is the same, different meaning. On-joint shear strength. So conclusions and remarks. Number one, laboratory physical model test and field trial in Hong Kong have demonstrated polio approach for dredged Hong Kong marine deposit slurry improvement or method. Okay, for improvement is effective. For laboratory, for the field trial, very effective. Can achieve the desired requirement. And poly-use sustainable reclamation approach can save a lot of money, reduce plenty of construction time, and with no carbon. We just use local materials, so that we don't need the manufacturer sand, And since Hong Kong Mineral Deposit doesn't have any monazite, so that Hong Kong Mineral Deposit is better than those sediments in Tianjin, Dalian. It's easier to get consolidated, achieve the high shear strengths. Cement and other binders, cement, other binders mixing with Hong Kong Mineral Deposit can be used at the key locations, not everywhere. If we use this mixing method for everywhere, the cost is very, very high, But at some key locations, which require high shear strength, you can do so, no problem, Not for everywhere. And all simple methods can be used to calculate the sediment, and we can control the post-construction sediment. The simple way to do so is to make the mineral deposit over-consolidated. It's very simple, There are a few numerical methods and simple methods, including proxies, can be used for calculating or predicting sediment during after construction, like proxies, you know very well. You can use that. And finally, I want to draw people's attention because I made a presentation of this in Hong Kong for the client, for the local consultants and people. So I want to emphasize again, main conclusion, quality control. Hong Kong mineral deposit is a good field material for Hong Kong because Hong Kong has never used Hong Kong mineral deposit as a field material so far. I want to promote this one. I want to convince them this is a good field material, So I need some time to convince them. So I emphasize this again. So actually it's a good field material, not bad. And there are many different soil improvement techniques. There are many, but I mentioned a few today. And so there are many already. What we introduced here is just one of them, like horizontal drain, market denoting, vertical drain. Maybe people use a different way. It's all okay. But no matter what kind of method you use, you have to make sure the post-construction sediment is small. Also, you can achieve required shear strength. So how do we know? So we control the post-construction sediment. We can make soil, the Hong Kong mineral deposit over-consolidated. If on the design node, because on the design node soil is over-consolidated. Second one, you can achieve OCR 1.3 even more. 1.3 probably is a good number. More, you need more money, more time. And you have to achieve average degree consolidation 92 to 95. So make excess pore pressure, most of excess pore pressure dissipated. So this is a good indication. The soil is a consolidation degree, this is a number. Finally, you can check the quality. No matter the contractors claim, I have done a good job, I have to do everything, according to the specification. I can check it. So you can do wind shear test to check on-drill shear strength, which can meet your requirements or not. So that's a fact. So the contractors cannot lie. You can check it as a consultant, as a client, you can check it. So this is a picture of the new regulation in Hong Kong for 1,000 hectares of reclamation. In the future, this is a natural island. They build 3 artificial islands around with a total area of 1,000 hectares. And nearly 500,000 people will live, in the 3 islands, So this is the picture of this new reclamation site. Thank you very much.
One's connection between the ASCE and the Greater, just only the last one. The ASCE and the Greater China section, what is?
Actually, ASC has a great channel. This is American Society, American Civil Engineering, American Society of Civil Engineering. Its headquarters is the USA, but there is a great China section in Hong Kong. Great China section in Hong Kong is the local chapter, including people in Hong Kong, mainland China, Macau, in Great China section. They are very active. They organize seminars, conferences in Hong Kong. This one is the Hong Kong Geotechnical Society is more related to international one. The member society of International Society for Soil Mechanics and Geotech Engineering is more international one. You are in the technical committee. Three. This is more USA international. This is local. there's a very powerful organization in Hong Kong. You get a chartership, everything is through this one. Hong Kong Institution of Engineers, the chartership, okay, license from this one. Hong Kong, this is our university, this is my department, this is our two research institute inside our university. Or this support our research, okay. This IC also UK one. Institute of Civil Engineering, UK, they also have a local chapter in Hong Kong, also very active. So this conference actually is an international symposium held in January this year, was supported by those organizations. So the final slide I show you, those supporting organizations, you know what I mean, okay?
So this is the landscape of the new area in Hong Kong?
Yeah, this will be a new area in Hong Kong. I think the construction was delayed because the economy in Hong Kong, and probably the real construction will start it in 2026. Before they said the construction will start 2025, but maybe delayed by 1 year. Maybe 2026 we will start construction. 1,000 hectares. Okay, so this is to solve the short supply of land problems and higher price for the property market. Okay, to solve the problems. But it's a very nice view. You can see there are many water channels, and there will be a beautiful town in the future in Hong Kong. Okay, any question? Oh, yeah.
That is great presentation.
Okay, good discussion.
Good discussion. Okay, should we stop the sharing?
We don't stop the sharing. Stop the recording.
Oh, yeah. How to do this?
Wait.
Okay, here. Stop recording. Disable. There. Pause recording.